Hi, dear students. In this series of video lectures, we are going to learn the paper called Modern Physics. It is a part of the 5th semester BSc Physics, and it is consisting of 4 units, and of which first unit is basically an introduction to the modern physics. I have divided it into 6 chapters like this, and each chapter will be covered in a separate lecture. Therefore, this current lecture, today's class, will be an introduction, and then you have photoelectric effect, Compton effect, de Broglie's matter wave hypothesis, group velocity and space velocity of matter waves, then Heisenberg's uncertainty principle, electron microscope in a separate lecture, and then I will be solving problems over 2 lectures in 2 sessions. So with the introduction, excluding the introduction, it will be a series of 8 sessions. Let us go through these one by one slowly. If you have any questions, you can post them in the comment below, or you can ask the questions through the WhatsApp or the phone number given here. You can also email me to the email ID provided below. You can ask questions, you can ask problems, not only related to the BSc Physics course. If you are writing any other competitive exam in physics, it may be CET, it may be IIT JAM or IIT JEE, or the entrance examination for the MSc, UGC NET, or any other entrance exam. As long as it is related to physics, you can ask questions, so no problem. So let us begin with an introduction to the modern physics. So why modern physics, and what is so important about it? Why do we have to study? Why this new name, modern? What is modern? Physics was a part of science. It was part of science for many hundreds of years. Probably the oldest subject, oldest scientific study was physics, when first man started making fire out of stones and made wheels. It was all physics, and then it developed all the way to here today, where we cannot live, we cannot do anything in our day-to-day life without the applications of physics. Until the 20th century, probably in the 19th century, everyone had thought that whatever is to be known is already known. So that means most of the phenomena that we come across around us were explained using the Newton's laws, and the laws written or understood by many others like Maxwell's electromagnetic theory, maybe thermodynamics, all these aspects of physics. Using them, people had understood almost everything. However, there were a few isolated experiments which could not be explained by the classical, we call that as classical physics, which was before 1900 approximately. So that was not explained by classical mechanics. One of them was the emission of electrons from a material, from a solid, when light is incident on it, which is later known as the photoelectric effect. It was seen by Hertz, but he did not understand what it is, and then it was finally explained by Max Planck, and of course by Albert Einstein in his famous photoelectric equation. Another one was heat capacity of solids. They could not explain, they could not clearly relate the theory and the experimental results of the specific heat of materials. They failed to explain the radiation coming out of a black body or a heated body. So which frequency has got what intensity? The intensity versus frequency of the heated object, like for example a heated iron rod, which is ideally treated as a heated black body. So that the spectra coming out of such objects could not be explained. They could not fit their equation to the observed values of the intensities of different frequencies. So for example, the red hot, the name itself says it's red. The red hot iron rod has got highest intensity at the frequency of a red light. Whereas if you heat it further, for example, the tungsten filament you see in the bulbs, it is white. Its temperature is higher than that of hot rod. That and then why or at what temperature, what is the maximum frequency? That could not be explained as well. Therefore, they were looking for alternative solutions to these, and of course, there were other aspects of science like the atomic spectra. You might have seen, you see two lines in the sodium vapor lamp, two intense lines called sodium D lines, which are as a result of atomic spectra. And that time in the 19th century, they had no idea of atoms or atomic orbitals. It was a vague concept. They didn't know because there were no microscopes or there was not enough theory to explain those aspects. So they could not explain the atomic spectra, the line spectra coming out of atoms as well. As a solution to this, scientists were thinking of different solutions, new theories, and then it was Max Planck came up with the idea of quantum theory approximately in the year of 1900. It was Max Planck. He was trying to explain the black body radiation, specific heat of solids. He was trying to explain the specific heat of solids, etc. And then he came up with Planck's law of radiation, which was explaining the output of a heated body. So he gave his views that the light is made up of quanta. So QUANTA, quanta, and he was the one who gave the equation energy of the electromagnetic radiation is given by h nu, where h is a fundamental constant which was basically invented by Max Planck. He realized that there should be a constant, Planck's constant. We are going to study its significance in later classes, and then this is the frequency. So energy of any light radiation is given by the frequency into the Planck's constant, and this h is of the order of 6.625 into 10 to the power minus 34 joules second. This is a very small number, remember, but it is significant. It is not zero. It has a weightage. Therefore, this equation was initially given by Max Planck. It is also known as Planck's quantum hypothesis. And after that, it was a breakthrough in the field of science and technology. Whatever we see today is a result of this quantum concept, the understanding of quantum physics. Maybe the mobile phones that you are using, maybe the Wi-Fi that is being connected to your phone. But the medicine today, the methods of scanning and lots of medicines, chemistry would not have developed to this extent without understanding the atom and atomic interactions. Chemistry means bonds, mainly bonds and reactions, and the basic understanding of chemistry lies in physics. Of course, biology, there would not have been the structure of DNA, RNA, or many other things related to biology. We would not have understood biology to this extent. Biological sciences, chemical sciences, lots of contribution from this, and that has made our lives better. I think so. So you can see my lecture because there was a person called Max Planck in 1900, and he invented something called quantum theory, as a result of which silicon transistors came into existence, and from transistors processors came to the technology got processors and memories, and of course lots of further developments in science and technology happened due to this. And of course it was not just Max Planck, there were many other scientists like Albert Einstein himself, though he did not believe in the quantum theory, but he is a great contributor to this quantum physics. And after that, lots of scientists, Louis de Broglie, Niels Bohr, Pauli, Heisenberg, Schrodinger, Richard Feynman. I mm, I cannot probably spell all the names. It would take a complete lecture just to spell all the names of the scientists who contributed or who developed the modern physics. So that is modern physics, starting with the invention of quantum theory by Max Planck, and it explains almost everything. It explains everything we see today or we witness today, starting from the RNA DNA inside our body all the way up to how why stars give light and what is the process happening inside the stars. Everything can be explained as of now with the fundamentals of modern physics and its applications. Some of the experimental evidences of necessity of modern physics, why quantum physics was necessary. There are, especially we are going to study two experiments in this uh, class, in this modern physics class. One of them is the photoelectric effect, where a metal object is irradiated with light, it emits electrons, and that was explained by modern physics. And then we are going to study what is known as Compton effect, where an electron is hit by a light particle like X-ray. When an electron is hit by an X-ray, the frequency of the X-ray changes and the electron is also knocked in some direction, and all this has a beautiful simple theoretical explanation we are going to see in the following lectures. And then we study also the atomic orbitals, atomic spectra and molecular spectra in the following units of this paper, modern physics. It is very interesting, very beautiful theory, and it is more than that, it is the fundamental of everything that we witness today. Therefore, concentrate on these, understand very well. If you have any questions, don't hesitate to ask. You can just send me a message privately if you don't want it to be discussed in public. And also, don't forget to inform your friends that such lecture series exists. And thank you for your attention. Let us meet in the following class with photoelectric effect. Initially it was by Hertz, and then it was explained properly by Albert Einstein. Probably the interesting thing is the experiment was done in sometime 1887, and Einstein explained it sometime in 1905. So it took almost close to 20 years to understand what is going on, and for that Einstein had the Nobel Prize for his photoelectric effect. Okay, have a nice time. Good luck.